Inside every single device you use, your phone, your laptop, your gaming console, there's a brain. It's called the CPU. And today we're going to pull back the curtain on the one single hidden principle that has powered all of them for the last 50 years. Let's dive in.
First, just to set the stage, you gotta see this leap. On the left, we've got the processor from the classic Apple IE. We're talking 1983. It had just over 4,500 transistors and could pull off a few 100,000 calculations a second. Now look at the right, a modern chip. It's got 16 billion transistors and can perform 3 trillion calculations a second. I mean, the difference in raw power is just staggering.
And yet, here's the crazy part. Despite being worlds apart, these two chips share a fundamental piece of technological DNA. They are built on the exact same core principle. So what is it? What could possibly connect the chip that ran the Oregon Trail to the one that's powering artificial intelligence today? Well, the answer isn't a physical thing. It's not the transistors themselves. It's not even the logic gates they make up. The DNA they share is a process, a fundamental rhythm that every single chip follows to get stuff done. To really wrap our heads around this, we're going to use a simple analogy. So for a minute, forget all the silicon and the circuits, and just picture a little robot working away inside of a giant library. So this entire library, the room itself, all the furniture, everything, that represents your computer. Every part of this scene is going to stand in for a real piece of hardware. First up, you've got these huge bookshelves that line all the walls. This is your computer's long-term storage, your hard drive, or SSD. It's where all your programs and files are kept, just like books sitting on a shelf. And then we've got this little cart. Now, it can't hold nearly as many books as the shelves, but whatever's on it is way faster to grab. This cart is your computer's working memory, your RAM. It's for all the tasks you're actively working on right now. Now, the table in the middle of the room, that's the main event. This is the central workspace where all the real action happens. This table is the CPU. And sitting on that table is a calculator. It can do all the basic math, adding and subtracting, but it can also do something really important: compare two numbers. This represents a part of the CPU called the arithmetic logic unit, or ALU for short. And finally, the star of our show, the robot. Its only job is to read instructions from the books and direct everything that happens in the room. This little robot is the control unit of the CPU. It's the manager, making sure everything gets done in the right order. Okay, and here is the absolute key to everything. Our robot, the control unit, doesn't actually do a million different things. It just follows a very simple 3-step cycle, over and over and over again, billions of times every second. And this cycle is the technological DNA we've been looking for. It's called fetch, decode, and execute. This is the fundamental heartbeat of pretty much every processor ever made. Let's break it down real quick. Step 1 is fetch. Simple enough. The robot goes over to the book it's working from, finds the very next instruction on its list, and brings that instruction over to the table. That's it. Step 2 is decode. Now the robot actually looks at the instruction it just grabbed. It deciphers the command to figure out exactly what it's being asked to do. Does it need to add 2 numbers? Does it need to store values somewhere? This is where it figures that out. And the final step is execute. The robot actually does the thing. It might use the calculator to do some math, or write a result down on a piece of paper, or go grab another piece of data from the cart. The task is done. And then what happens? The cycle starts all over again. Fetch, decode, execute. So that's the big reveal. That simple 3-step loop is the fundamental process that connects that little chip from 1983 to the supercomputer that you have in your pocket today. Now, you might think the instructions themselves must be really complex. But get this, the original processor in that Apple IIe only understood 56 different commands. That was its entire vocabulary. So what about a modern processor? Well, it's definitely more capable, but it still only understands a few hundred instructions. This one has 354. It's a surprisingly small toolbox when you think about it. Just let that sink in for a moment. Every single thing, from rendering a mind-blowing 3D world in a video game to literally just moving your mouse cursor across the screen, it's all just a long sequence of these super simple instructions, executed one after another at blinding speed. So if the process is so similar, where does that 10 billion-fold power difference come from? Well, the biggest factor is just raw speed. The old chip ran that fetch, decode, execute cycle about 1,000,000 times per second. A modern chip runs the exact same cycle over 3 billion times per second. On top of that, modern chips have all these clever tricks to make the cycle even faster. Pipelining is like having an assembly line of robots. One is fetching an instruction while another is decoding the last one, and a third is executing the one before that, all at the same time. Larger caches just mean the robot can keep its favorite books right there on the table instead of running to the shelves. And branch prediction, that's like the robot getting so good at its job, it can actually guess what instruction you'll need next and fetch it ahead of time. It's all about making that loop brutally efficient. And really, that's the beautiful secret at the heart of it all. Our entire digital world, from the simplest games of the past to the most complex AI of today, is all built on that same elegant three-step dance. A process so fundamental it's been the bedrock of computing for half a century. It's just an incredibly powerful and timeless idea. Which, of course, leaves us with one last, fascinating question to think about. If this simple cycle has gotten us this far, what new fundamental process, what next technological DNA is going to power the world of tomorrow?